All right, time for more fun with the problem sets. Problem set number 2. Where does the derivative equal 0? So here's the function that I'm talking about, and we'll use the power rule to take the derivative. So we've got 3x squared. For this, bring the 2 down. That's going to be minus 16x, and then plus a 7. Now set it equal to 0. And in order to solve for x, we get to use the quadratic formula. So there's the a, the b, the c. X is equal to negative of the b plus or minus the square root b squared minus 4 times a times c, all divided by 2 times a. So of course I'm going to use a calculator, but I want to simplify it a little bit first. So this is going to be a positive 16 plus or minus, what is that, 256? Oh, it's got that weird glare on it. Let me hold it like this. It's still not great, but 16 squared. So the negative gets squared, so it turns into a positive 256. And then minus 4 times 3 times 7. So we've got the square root of 172. And it's divided by 6. So let's see, 16. Oh, I should put parentheses first. 16 plus the square root of 172, and that gets divided by 6. But I put the whole thing in parentheses, so the whole thing gets divided by 6. Now I'm just going to use 3 decimals, so that's 4.852. And let me just change this back to 3 decimals. And then go second enter to get it back. And now change this to minus the square root of 172, a point 481. Okay, so those are the two x values. Then I also want to graph it and show where the derivative equals 0. So I go to y equals the glare. And here's the original function. I could then go to zoom 6, and right there the derivative equals 0 when it got to the top of that hill. It then went down off the screen. When it gets to the bottom, that's where the derivative equals 0, and then go back up. So I need to change the window. So this part down here is going, if you go to trace, and you don't even have to look at the cursor, but just look at the y values, it'll tell you how far down it's going. So it's negative 29, 37, 38, 39, 40. It went to about negative 41. So I'll put this at negative 50, and then I should be able to see the whole graph. So it looks approximately like this. So right here, that's one place where the derivative equals 0, and right here, that's another place. Then trace, and I got an answer of 0.481. So this point is, x is 0.481, and y is just a 0.627. Okay, that one's done. And now the 4.852, yep, that's at the bottom. And so this point is, x is 4.852 and y is negative 1.146. So this is called a local maximum when it reached the top of that hill, and this is called a local minimum when it reaches the bottom of that little valley. And the derivative tells you when that happens. Now I know what you're thinking. How about some trigonometry? Excellent idea. So for example number 2, we're going to do the same thing, but the function is going to be cosine of 2x on the interval from 0 to pi. So take the derivative. The derivative of cosine is negative sine of 2x. And then do the chain rule, take the derivative of 2x, which is a 2, and you multiply by that 2. Then set it equal to 0, and I'm just going to move this 2 to the front. And basically this is just saying when does sine equal 0? Because this negative 2, you could just divide both sides by negative 2. It's still going to say 0 equals, and then all that's left is sine of 2x. Now the way that I do it is I ignore the 2x for a moment, and it just says when does the sine graph equal 0? So the sine graph looks like this. So right here at 2 pi, right here at pi, and right here at 0, those are all times when the sine graph equals 0. Now pay attention to the 2x. So that means 2x equals this, or 2x equals this, or 2x equals this. So you'd have 2x equals 0, 2x equals pi, 2x equals 2 pi. And then for all of these, divide by 2 to solve for x. So the first one is going to be 0. The next one will be pi over 2. And the next one, the 2's will cancel, and that'll just be pi. Which turns out to be perfect because the interval said go from 0 to pi. And then graph the function and let's see what's going on. So always graph the original function. Cosine of 2x. Change the window to go from 0 to pi, and then pi ranges from -1 to 1. So it's at the top of the hill right there, so that's one answer. It's at the bottom of the valley right there, and it's at the top right there. So this would be 0, this would be pi over 2, and this would be pi. Now graph it and label. So the function looks like this, and then label the 3 answers. So that one is when I put trace and 0, that point is 0, 1. And then pi divided by 2. So once you've pressed trace, you don't have to press it again unless you leave the screen and come back. So that would be pi over 2, comma, -1. And then this one, well, it should be at pi, comma 1. So put second pi, and sure enough, that's pi, comma 1. Okay, now how about something that is a rational function? So for example number 3, and this time I'm asking, where is the derivative positive? I know what you were thinking. You were thinking I was going to say, where is my super suit? Now usually I do all of the work first and then I use the calculator at the end, but you don't have to do that. As long as you end up showing your work, that's fine. So I'm going to check out this function and see what's going on. So x gets divided by, and the denominator needs to be in parentheses, x squared plus 2x plus 1. And then take a look at the graph. So I'm just going to go zoom standard or zoom 6. So the derivative tells you the slope of the tangent line. Basically, this is saying when is slope positive? Well, slope positive means that the function is going up. It doesn't have to be going up that steep, but as long as it's going up. So where is it going up? So this is going down, 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 down. Looks like it goes down to infinity. It's got an asymptote right here at -1. I could prove that if I put trace -1 and it says a blank. So that means there's an asymptote at -1. So here's the -1, and on paper, the way that we show there's an asymptote is you use the dotted line. So this side is going down, and then this side is going up, and then it looks to me like it peaks out somewhere in here as the tallest point. So I think I'll need to zoom in on that a little bit. Zoom in on this area and see what's going on in there. So it peaks out somewhere in here, somewhere around 1. So it goes up. I'm gonna over exaggerate it, that it looks like this. So it peaks right about there. So that means this is going up and going up and going up and going up, and then it's gonna go down, down, down. So the answer to the question is, in this area right here, this is when the derivative is positive, when the function is going up. Now we need to actually do the work. Or should we call it the fun? So this is a rational function. That means we need to use the quotient rule. So to find the derivative, it's going to be, of course, it's going to be a quotient. And you start on the top. The derivative of x is 1, and then leave x squared plus 2x plus 1 alone. Minus, now leave the x alone, and take the derivative of this. Derivative would be 2x plus 2. And then the denominator gets squared. Now we need to solve for x. Well, let me tell you something. When you have the derivative, and it's a rational function or a fraction, if you set the bottom equal to 0, that is where the derivative is undefined. So that would be like right here at -1. But we don't need that point, we need this point. And right here, the derivative is defined, and that's going to come from when the top equals 0. So we actually don't even need the bottom, we just need the top equals 0. So for the top, multiply by 1, so that's x squared plus 2x plus 1. Distribute this negative x, so that's going to be negative 2x squared. And then negative 2x. And then that's set equal to 0. So combining x squares, there's going to be negative x squared. Oh, nice. These two cancel. All that's left is a plus 1. And then I could move the x squared to the other side, making it a positive x squared, and then take the square root. When you take the square root, don't forget to put plus or minus. And so x equals both plus 1 and minus 1 are important numbers. So the minus 1, we already had that figured out as an asymptote. So it turns out that this point right here, that is at 1. Now I can check my answer. So when I go to this 1, and I tell the calculator find the derivative, it should tell me the derivative equals 0 right there. So I go to second calculate, and then number 6 is the derivative. Plug in the number 1, and it says you were right, the derivative equals 0 right there. And it even tells me what x and y is. So this point right here is 1, 0.25. Now I need to look back and see, did I answer the question? Well, I did in words, but I didn't write it down. So for the final answer, y prime is positive on the interval. So when it says where, as far as this is concerned, it's saying for what x values. So from x is a -1 until x is a +1, this is the only time when it's going up. So on the interval from -1 to +1. And these should both have round parentheses, not a square bracket. Because at this point, it's got an asymptote, so the function doesn't even exist there. And at this point, it's at the top, so it's not going up anymore. So you don't include the 1 itself, you just put a round parenthesis. And then just one more. Example number 4. In the year 2000, the US population, and I just Googled, obviously, US population 2000, and it told me the 2000 census said the US population was 281.4 million people. Oops, in 2020, it is 328.2 million people. So it's grown by, what's that, 19, it's grown by 28, 38, 48, 47, about 47 million people. That's a lot. That is exponential growth. Since it's exponential growth, we're going to be using the PERT formula. Hopefully you remember that one from pre-calculus. And with the PERT formula, this is the beginning population. That's the 281.4. The R is the percent that it's growing each year, not over the 20 years, but each year. So that was not given in the problem. And T stands for time. So as you could see, that's 20 years. And this is the ending amount, which will be the 328.2 million. So the P is the beginning amount, and then E to the R, and T is 20 years from the year 2000 to 2020. And then we need to solve for R using some pre-calculus. First, divide both sides by 281.4. These will cancel. And then this part, don't even divide, don't literally divide and get a decimal. Just leave it as it is, because we're going to type it in the calculator in a moment. All right, the next thing is we need to eliminate E. And the way to do that, use natural log. These two are inverses of each other, so they cancel each other out. And then it's going to be natural log of this, 328.2 divided by 281.4. And last, divide both sides by this 20 right here. I wish I could just cut and paste on this paper, but it's not smart enough. Or maybe I'm not smart enough. Well, anyway, I can just type this in a calculator now. All right, so it's natural log, so ln, of 328.2 gets divided by 281.4, close the parentheses, so all that's inside the natural log, and then divide by 20. So R is equal to 0.008. So if you multiply this by 100 to change it to a percent, that means the United States is growing, or at least has been growing by just 0.8%, a little bit less than 1% per year. Or in other words, the growth formula is going to be the starting number. So I'm just going back to this right now. So that's a 281.4 e to the 0.008 t. So that's the function that will predict the population of the United States in the following years. Now, for the calculus part, because all of this has been pre-calculus. So now finally, it's time to do a derivative, which is the calculus part. So find the derivative. That is the easy part, because the derivative for the e function is just itself. Just copy down the whole function. Then we still need to do the chain rule. So take the derivative of this. Since t is the variable, its derivative is going to be a 1. So we get 1 times this decimal. And then the chain rule says you need to multiply by that. The next part is plug in a 10. Copy down everything else except plug in a 10. And what does that equal? So we have a 281.4, and then it's e to the 0.008. That's times a 10. And then move to the right, put parentheses, 0.008. And keep in mind that this is in millions, so that means approximately 2.5 million. So it's 2.434 million, or 2,434,000. All right, so we found the derivative, but what does it mean? Well, for one thing, 10 means 10 years after the story started. So it started with the 2000 census, so that means 10 years later would be 2010. And then this is population growth. So derivative means how fast is it changing. So that's how fast the population was changing in 2010. In other words, there was about 2.5 million new people, whether they were born or immigrated, or how else? Oh, they could apparate. Anyway, there's new people that came to the United States in 2010. In 2010, the US population was growing by 2,434,000 people per year. And I say, welcome to all of them. Come on in, grab a cup of coffee. We got a place for you to stay. All right, I'll talk to you again soon.